Hello everyone. Today I'll be talking about functorial data integration. So let me see if I can share my screen. All right, you are screen sharing. Great. Okay, so as I mentioned, the topic today is functorial data integration, and it is a continuation of the previous talk that we had on functorial data migration. So in this talk, we'll do a brief review of functorial data migration, talk briefly about the difference between migration and integration, and then talk about a technology called pushouts that categorical informatics uses to do data integration. So why the distinction between migration and integration? Well, if you recall from the previous lecture on migration, we have these delta sigma pi data migration operations. These are unary operations, and in data integration, we typically want to combine more than one data set, so we need operations that are binary operations in order to do true integration. So that is why there is a distinction. So let's start by reviewing the functorial data model from last time. So the slogan here is that categories are schemas and vice versa, and we present schemas in the functorial data model using this graphical notation where every node you can think of as an entity. So in this example, we have employees and departments. The edges represent foreign keys. So in this case, manager takes an employee to an employee, works in takes an employee to the department that they work in, and secretary takes each department to the employee that is their secretary. There are path equivalence constraints that are data integrity constraints or business rules on the schema. So here, for example, it says that a department secretary must work in that department. That's the one on the right there. And the one on the left says that an employee's manager must work in the same department that the employee does. The open circles in the graph there are the attributes. So employees have first and last names and departments just have regular names. And an instance, which categorically is a set valued functor, can be thought of as just a set of tables where each node corresponds to one table and the columns in the table correspond to the attributes and foreign keys. So for example here, employee, the table there has 3 employees, 101, 102, 103, with the manager column filled in appropriately. You can see first and last names, and similarly there's department, 2 departments, CS and math, and you see the foreign key secretary abbreviated there, which is foreign keys back into the employee table. So what can you do with schemas as categories? Well, you can migrate data from one schema to another using a concept known as a functor. So a functor from schema S to schema T, it is a path equality constraint respecting mapping. It takes nodes in S to nodes in T and edges in S to paths in T. And the key idea here is that for each functor F, there are 3 induced data migration operators. Delta, which goes backwards, it takes instances on T to instances on S, excuse me. It's a projection-like operation. And pi and sigma, which go forward, they take instances on S to instances on T. And these are like a join and a union kind of operation. So the details of these are described in the previous talk. I wanted to review them here because we will be seeing a bit more of these operations when we start to talk about doing functorial data integration, which we will do now. So what is data integration? Well, at a high level, it's simply the process of combining 2 or more data sets into a unified other data set. So for example, you have data for Exxon and data for Mobil. These are oil companies. They were oil companies. And they merged, and so they had to merge their IT infrastructures and their database systems into ExxonMobil. That is one particular example of data integration. Another example is you might have terrorist events and weather data sitting in their own separate databases, and you might want to unify them, integrate them to try to understand how weather affects terrorism. So again, just two databases being merged and integrated into a third. So categorically, that process of merging, it is modeled by a construction known as a pushout, and that works very similarly. So suppose we have two databases here, database 1 and database 2, and we have an overlap between the two databases that specifies the entities they have in common. Actually, I should be more precise, that specifies relationships between the entities that might indicate an overlap. In this talk, I will not dwell too much on the details of what an overlap is, but we'll see an example in a minute. The pushout is a database instance that is relative to the overlap. So here P is the integrated database. So this diagram means that if you start at the overlap and you go from the overlap into database 1 and then into the pushout, you get the same answers if you go from the overlap into database 2 into the pushout. So that's one of the correctness criteria for integrating data correctly. But pushouts have what's called a universal property, which means for any other integrated database, so in this case X, there will be a unique way to get from the pushout to that other integrated database. So this is one reason why we say that our categorical technology gives the best possible solution. In this case, we'll be using pushouts to integrate data, and they are universal among all possible integrated databases. So with that in mind, for the rest of the talk, I'm going to be going into an extended example, but a few remarks are in order. So pushouts are a category theoretic construction. They can be defined in any category, but they need not exist. They exist at both the schema and database level in our FQL tool, and the tool will compute them for you. And to do that requires using sophisticated automated theorem proving techniques. And those of you who are familiar with relational database theory can compare our pushout technology to something called the chase, which is sort of a similar kind of technique that pops up in relational database theory. So here is the overview of how to use pushouts for data integration. This slide looks kind of intense, but we will do an extended example in just a moment that will make this more intuitive. So here I will just sketch this example, and let me mention now, if you go to the end of the slides, there's a link to a paper that writes out as text much of what I'm going to say now. So that is available to anyone interested. So the pattern works by first taking two input schemas, S1 and S2. So you can think of that as the database schema for Exxon and the database schema for Mobil, and an overlap schema, as well as mappings from the overlap into the schemas. We first push out those schemas to get an integrated schema. So you can think of that as being the schema for the integrated ExxonMobil information. So step one, we do integration using pushouts on schemas. Then in step two, we use pushouts to integrate the data. So here the input is an instance on S1, so this would be Exxon's actual data, I1. An instance on S2, so that would be Mobil's actual data. And here we give an overlap as an instance on S and morphisms of databases H1 and H2 that specifies the relationship between them. And then we do the push out here to get the integrated instance on the ExxonMobil schema. So that is a lot of math, but the point here is really that this is a design pattern. and that it's not necessary to understand anything that I just said to use this. So in particular, the input to our design pattern for data integration is one schema, two schema mappings, one database instance, and two database mappings. So if desired, the input schema and the mappings, they can be constructed automatically using schema matching techniques. These are well studied in the literature. And similarly, the overlap database instance and the morphisms of databases can be constructed automatically using data matching techniques, which are also well studied in the literature. So these are essentially the knobs you have to twist. So if, to summarize, we assume that two input schemas S1 and S2 are fixed and two input instances on those schemas are fixed. And then the knob that you have to turn to specify your data integrations is one other schema S, two mappings F1 and F2, one database instance I, and two morphisms or mappings of databases. And that's the space in which we're working, and if necessary, those can all be computed automatically. And the output of this design pattern is an integrated schema, which we'll call T, and an instance on that schema that is universal among integrated instances. So what does that look like? Here is an example of the push-out pattern, first at the schema level and then at the data level. And this is described in a paper which you can find on our website called An Equational Formalism and Design Pattern for Functorial Data Integration. So this slide here is showing an example of a schema level push-out based integration that is based on medical records. So there are 4 schemas and 4 mappings on this screen. The one in the lower left and the upper right are the schemas that the input to our pattern are on, and the schema in the upper left is the overlap. And the schema in the lower right is the pushout. It's the integrated schema. So this is medical records data. So as you can see in these schemas, there are entities for patients. There are also an entity called observation, which represents observations that are done on patients, for example, taking their blood pressure or their weight, and that there are paths in these schema to go from observation to the types of observations that are done, for example, blood pressure and weight, and that in one of the schemas in the lower left, there's an entity called method, which you can think of as being the method by which the observation was taken. So for example, patient self-report or a blood pressure cuff or a nurse or what have you. So the idea here is that we have 2 schemas in the lower, one in the lower left, one in the upper right, that are talking about similar kinds of things, patients and observations that are done on them, where observations have types like blood pressure and weight, and that we want to try to integrate data that's on each of these schemas. And so we start by integrating the schemas themselves, and this here, this particular diagram shows how to do that. So step 1 to integrate the schemas is we need to come up with an overlap schema that relates them. And so you can do this by either automated techniques. For example, you can recognize that observation has the same name in the 2 input schemas, but for us, we'll just talk through it. So we see that the here we've chosen for the overlap schema to consist of 3 entities, O, P, and T. So O corresponds to observation in both, P corresponds to patient in one and person in the other, and T corresponds to type in one and obs type in the other. And in this diagram, we've labeled with colors, red, green, and blue, the various ways in which these mappings are taking place. So for example, we have an edge F going from O to P in the overlap schema. That gets mapped to the edge, or really the path of length 1 in the lower left. It gets mapped to another path F that goes from observation to patient. And G, the edge from O to T that is green in the upper left, goes to the path G1 followed by G2. So observation goes to method by G1 and then to type by G2. And that attribute hanging off of T, that's the text that describes the type, blood pressure, body weight, what have you, also goes to that attribute in blue down there on the lower left. And a similar thing is going on with the mapping from the upper left into the upper right, except here it's a much more direct mapping because F goes to F, G goes to G, and T goes to, or that attribute goes to that attribute. It's essentially an inclusion mapping, although note that there's gender information in the schema on the upper right that does not exist in the schema in the lower left. And then finally, note that the overlap schema in the upper left, it has an attribute hanging off T because in this example, we're going to think of the types of observations that are done, for example, blood pressure and body weight, as being a controlled vocabulary. So we expect the terms, for example, blood pressure and body weight, to be the same across the input data. There is not an attribute in the upper left for patient, but there are attributes for patient and person, and the reason is that we don't expect that the names of the patients will be the same between the databases. So for example, in database 1, a particular patient may have a name of Pete, and in database 2, they may have a name of Peter, and we don't want to assume that these names are the same across the databases, and so for that reason, we don't include an attribute in our overlap schema. So anyway, once we have created our overlap schema as shown here and created the mappings, the tool computes the pushout of that overlap, and it shows it in the lower right. And so what does it look like? Well, it has the same observation, person, and type nodes, but it has other nodes as well. So for example, it has method. It picked that up from the schema on the lower left, and it has gender. It picked that up from the schema on the upper right. And it also has 2 attributes for patient, the idea being that a patient can have different names in different databases, so we need 2 attributes. One attribute says this was the patient's name in database 1, the other attribute says this was the patient's name in database 2. There's only one attribute for type though, because we had an attribute for type in the overlap schema, and that means that this is a controlled vocabulary, and so it's redundant to record that the type in one was blood pressure and the type in the other is also blood pressure. So anyway, this is explained in more detail in the aforementioned paper that I would encourage everyone to check out, because it is difficult to do justice to this verbally. And so what does it look like when we do the pushout-based integration of the data itself? Well, this is another pushout diagram. So there are 4 things with an overlap in the upper left and the inputs in the upper right and lower left. And then a integrated pushout in the lower right. So let me talk through this. In the lower left is a particular instance that we made up to be indicative of a database here. And so you see tables for observations and methods and types and patients. So here we have 2 patients, Jane and Pete, and our controlled vocabulary for types of observation is just blood pressure, that's BP, and weight. In the upper right there is a similar schema, or an instance on the other schema that has a similar kind of data. So here this also has gender information, male and female. It has 2 persons, Paul and Peter, and 3 types of observations, blood pressure, weight, and heart rate. So those are the inputs in the lower left and in the upper right. And in the upper left is a overlap instance that we have to give to do our integration. So here, for purposes of exposition, we have chosen to have no observations in common between the 2 instances. We've chosen to have 1 patient in common, so that's we indicate by P, the ID P. It's red, and you'll see that in the lower left it corresponds to Pete. You can see that in the patient table. In the upper right it corresponds to Peter in the person table. So the idea here is that the map from the upper left to the lower right sends P to P, and the map from the upper left to the upper right sends P to P, and that P represents the same person that's in 2 different databases, even though the attributes of that person are a little bit different. So Pete in one, Peter in the other. And then finally, the overlap instance, the table T, has 2 terms, words, phrases, blood pressure and weight, in common between the 2 input instances. So those are in blue. And you see that those 4 entries, BP, WT, and weight, occur in the upper right and the lower left. So this is a relatively simple overlap instance. It just says that we have 1 person in both that we call P, and that we have 2 kinds of types in common in both inputs, blood pressure and weight. So you give this information to the SQL tool, and it computes the pushout of it and shows it to you as in the lower right. So what does that look like? Well, we can start by noting that the observation table, there were 4 things and 3 things and none in the overlap, and so we end up with all of those in the overlap table O in the pushed out thing. And a similar, let's see, okay, so 7 things in O. What else is there to notice about the lower right? Well, one thing to notice is that in the P table, we have Jane, who came from one but not the other. We have Paul, who came from one but not the other. And so in particular, each of those, they have one attribute that gives their name in the table, in the source that they came from, and the other attribute is null. And that Pete has, or who we were calling P, there's only one of him. So, and here his ID is PE, and he picked up an attribute Peter from the one database and the attribute Pete from the other. So this correctly integrated this one entity that was in the overlap of both, and for the other ones, it copied them over and then left nulls essentially in their attributes. So an interesting consequence of this actually is that there is now, because of this, an additional gender. So in the input data on the upper right, we had F and M, male, or excuse me, female and male. And in the integrated data, we have a new gender that is not one of those. That is the gender for Jane. So you can see IDJ for Jane, attribute to Jane. The H column is what is sending it to gender, and since Jane came from a database that had no conception of gender, the tool created a new one for her. So that's why there are 3 entries in G. So this does what you might expect. It forms intuitively the smallest union relative to the overlap possible and then fills in missing information such as the new gender as it has to. And this process of filling in that information is what's related to Chase from database theory. But anyway, I would encourage everyone who's intrigued by this admittedly hasty description to take a look at that paper and read about this at their leisure. So here in the conclusion, this is that archive reference to that paper to read about it, and then the example is also included in the FQL tool. So anyway, to summarize, the category theoretic technology that we have built in the FQL tool can do more than just migrate data from one schema to another. It can integrate data across various schemas, and that uses a new kind of construction that we call a pushout that has been well studied in database circles, and that we have a design pattern to do data integration that uses pushouts twice. First, we use it to integrate the input schemas, and then we use it to integrate the input data. And yeah, everyone, I would encourage to check out the paper listed there. So that's it for this talk. Thank you all for listening.